Hello everyone, I am Abdullah Abuolaim and I'm going to present our ICCV paper, Learning to Reduce Defocus Blur by Realistically Modeling Dual-Pixel Data. This work is done with Mauricio Del Precio, Damian Kelly, Michael Brown, and Payman Milanfar. Now, I'll start with the Dual-Pixel Sensor, or DP sensor. This sensor provides two photodiodes at each pixel location as shown here. And when subsampling the left and right photodiodes, we get two sub-aperture views at single image capture. These views exhibit a difference that is correlated to the amount of defocus blur. Last year, myself and Michael demonstrated that DP data can provide useful cues for defocus deblurring in a data-driven approach. This data-driven approach required us to capture two images for the same static scene at different aperture settings. One with the spatially varying defocus blur and its corresponding dB views, and another all-in-focus image. However, this approach requires careful setup to avoid any misalignment within image pair capture. And while most of the modern cameras employ DP sensors, only a few provide accessing to DP data for camera users. Another challenge is that no camera allows users to extract DP data for videos. To address these challenges, we propose a DP data synthesis framework that realistically models the DP image acquisition process. Such data synthesis framework helps us to mimic other cameras and allows us to generate DP data for videos. To start the effort towards synthesizing DP data, we utilize the computer-generated Cynthia Street View dataset. As shown here, this dataset provides all-in-focus video frames with their corresponding depth maps. For this data, and by utilizing a thin lens model with certain camera parameters like focal length, aperture size, and focus distance, we can obtain a defocus map from the given depth map. Then, given the defocus map, we realistically model the aberrated point spread function PSF or the blur kernel using a 2D Butterworth filter, in which it allows us to generate PSFs similar to what we find in real dual-pixel sensors as shown here. Then each pixel in the all-in-focus image is convolved with our DP PSF according to its value in the defocus map. Convolving with the left DP PSF will generate our DP left sub-aperture view. Then the same is applied with the right DP PSFs in order to get the right view. Now, we alternate between the generated DP views in order to visualize the difference in phase. This animation shows that our generated DP views exhibit difference similar to what we find in real DP sensors, where the scene points kind of rotating around the focal plane. Now, we apply radial distortion on the generated views to mimic the radially distorted images obtained by real cameras. So, in this animation here, we show the image before and after applying radial distortion. With our DP data synthesis framework, we are able to generate video frames along with their corresponding DP views. This will allow us to explore a new domain application that is video defocus deblurring, and the network is designed based on that. We propose our recurrent DP defocus deblurring network, RDPT, and we selected recurrent network as it allows training with variable input frame size. The training data is a mix of real single images from Canon camera and our synthetically generated video frames. With that said, in the training phase, we can interchangeably train with a single image or video frames at each iteration. Such iterative training between single real image and time series synthetic data is very useful to learn deblurring at different data domains and give the network the flexibility to deblur for a single image as well as an image sequence. We added convolved TM unit at the bottleneck to enable a recurrent network. We picked convolved TM over other recurrent options as it keeps our network fully convolutional and helps in learning long-term time dependency in the image sequence. In addition to the traditional L2 loss between the RDPT output and the ground truth, we also penalize image gradients for multiple operator directions and scales as animated here. Our new multi-scale edge loss encourages the proposed model to better learn restoring sharp edges and high frequencies. While we follow the common practice of batch-wise training, we are aware it is also important to have the radial distance from the image plane center. Therefore, to address this, we also feed the corresponding radial distance patch for each input image patch. Here, we report in this table the quantitative results of various defocus deep learning methods tested on the Canon DP dataset. Our RDPD network outperforms other methods for the PSNR, MAE, and the perceptual metric NIQE. It's also worth mentioning that our RDPD is lighter weight and has an inference time that is 2 times faster than the second top method. Here, we show qualitatively that our network generalizes well for other cameras that are not using the training data. Thanks for your interest in this work. You can also scan the QR code here to visit the GitHub page for the code and dataset.